Mahsa, Derakhshan. We'll talk about stochastic minimum vertex cover in general graphs, a 3/2 approximation.
Thank you for the introduction, and thank you for inviting me. There's echo here. Okay, good. Yeah. This is based on the joint work with Navin Durvashila and Nika Haqtalab. Am I speaking loud enough? Yeah? Okay. It could be louder. Good. Yeah, so it's about stochastic minimum vertex cover in general graphs. What we refer to as the stochastic graphs here are basically a generalization of random graphs where edges can exist with different probabilities. Right? So the definition is based on a base graph G and a probability P sub E for any edge. Then each edge of this base graph is realized independently with those probabilities, forming our stochastic graph GSR, or I may also refer to it as the realized graph. Okay, so let's say this is my base graph G, and all PEs are equal half. In that case, an instance of my realization would be something like this. Each edge exists independently with probability half. Now, in this workshop, we want to talk about simplifying the stochastic graphs. So we have our parameters, base graph, and probabilities. And we want to query a few edges of this graph or a sparse subgraph in order to find a good solution to whatever problem we want to solve. Okay. And our goal is to find a good approximate solution. Here, querying is basically, okay, let me be more clear. So your input is your base graph and probabilities. You don't know which edges actually exist. You query it, and you see whether it exists or not. And based on that information, you want to solve your problem. The problems studied here in this model are, spanning trees, shortest path. The most studied one is maximum matching. I'll show you a list of results. And the one I'm going to talk about today, which is minimum vertex cover. Matching is also the one most closely related to minimum vertex cover. So I'll just briefly show you a list of results. And generally, we want the number of queries to be linear in n number of vertices. And P here is a parameter that's the minimum existence probability over all the edges in the base graph. Or for simplicity, you can just assume that all the probabilities are the same for the ones that are in the base graph. So any edge that's not in the base graph will not exist in our stochastic graph. Okay. This was just about matching. Now let's go back to our problem vertex cover. Vertex cover of a graph is basically a set of vertices that include at least one endpoint of any edge. And we are interested in finding the smallest vertex cover, and we'll approximate that. The known results for stochastic vertex cover are just these. For general graphs, we have almost 2 approximation. And for bipartite graphs, we have better results, but they achieved basically using known results for matching. Now, the question that we asked today is whether we can improve over this 2 approximation for general graphs. And we are interested in having this many queries, or we want to query a graph with this many edges, because that's the smallest number of edges required. So to get any constant approximation, we require querying at least that many edges. We want to see what we can get using that many queries. So we know that to beat half approximation for a minimum vertex cover, based on Games conjecture, you cannot do that in polynomial time. So we are not attempting to design polynomial time algorithms. As even this model itself is more like information theoretical question here that we are asking. We are not concerned with computational, with having polynomial time algorithms. And interestingly, this problem is the first computationally hard problem studied in this setting. All the previous ones were had polynomial time algorithms, and those actually kind of guided the design of algorithms in this model, like having a small augmenting path, for example, for matching. But here we have to come up with something new. The results we have in this work are, first, we have a 1.5, almost 1.5 approximation using optimal number of queries. And by optimal, I mean you need those many queries to achieve any constant approximation. And here again, P is the minimum probability of existence over all the edges in the base graph. And we also show that to beat this 1.5 approximation, you have to rely on the fact that edges exist independently, because if O of n edges are allowed to be realized in a correlated way, this 1.5 cannot be broken. And interestingly, the argument is based on RS graphs, and it's very similar to what Sanjeev and Sepper and Lee had for the stochastic matching problem. Now, let me go over the problem again formally and talk about algorithms. So our input is, again, our base graph G and a parameter P sub E for the existence of each edge. Edges are realized independently with those probabilities, forming our stochastic subgraph G star. And we can query the edges to see whether they exist or not. And based on that information, we want to find a small vertex cover. Something that's kind of special about minimum vertex cover is that if I don't query an edge, I have to cover it, right? Because I want to make sure that my solution is a valid vertex cover. So if I don't query an edge, it should be covered in the final solution. So basically, I need to pick a sparse subgraph edge of my base graph, such that after querying that, the solution is not too large. So what's the solution? I have to, H star is the realization of all the edges that I query, and R is all the edges I don't query. So what I output is the minimum vertex cover of these edges, right? And I want that to be small compared to the expected size of the optimal solution, which is a minimum vertex cover of G star. Any questions so far about the model?
If all the edge probabilities are the same, that makes
No, it doesn't, yeah. So I'll first start with two approximation algorithms, which are simple, and they kind of behave differently. One is good for some specific instances. The other one is good for kind of opposite instances, and then see how we can mix them to go beyond two. The first algorithm is as follows. It starts by drawing a random realization of the base graph, which is referred to by G1. This is going to be from the same distribution as G star. Okay. The way we construct it is that we draw each edge belongs to G1 independently with probability P sub E. Right? So G1 is from the same distribution as G star. Then we pick a minimum vertex cover of G1, which we refer to as P, right? And we commit to have all these vertices in the final solution. Right? So after you commit these, you don't have to worry about the edges that are connected to these vertices, right? So you only query the induced subgraph of G over the rest of the vertices. And then what you output is the union of P and the minimum vertex cover of all the edges that we queried and were realized. Okay, so H star is the realization of H. Now let's see how the algorithm works on this graph. This is our base graph G. We randomly realize these edges. So here at this point, I'm not querying anything. Right? So I'm just drawing a realization of it over my base graph. Okay. So my random realization, take a minimum vertex cover of it, the red vertices. I just eliminate them because they will be in the final solution. Now I need to worry about the rest. H. I query those. I get H star, also cover these. and I'll output the union of the green and red ones. Right. So I have to answer two questions. First, why is it that H is sparse? I didn't say anything about that. And the second thing is that, okay, why is it a good approximation ratio? Okay, let's first answer the second question. So first of all, P here, as I mentioned, okay, G1 comes from the same distribution as G star, right? So P also comes from the same distribution as opt, right? So it has the same size as the optimal solution. So the number of vertices I add here to the final solution is basically opt, right? Now, in the second step, what we add to it is a minimum vertex cover of H star. H star is basically a subgraph of G star, right? So here, again, what we add is, at most, the size is opt, right? So it's very easy to see that it's basically a two approximation in expectation. Right? Now let's see why H is sparse. I claim that it has O of n over P edges. So it's basically a simple application of union bound. First of all, H is an induced subgraph of G, right? Because we first committed some of the vertices to the final solution. Now H is the induced subgraph for the remaining ones. How many possibilities we have for that? 2 to the power of n. The second fact about H is that none of its edges are realized in G1, right? What's the probability of that happening? If it has X edges, that's going to be, okay, here I'm assuming that the probabilities are all the same, so let's go with that. The probability of none of them being realized is 1 minus p to the power of x. So we can see that with high probability, the number of edges that H has is smaller than n over p. Okay. So now, to be able to compare this one with the second algorithm that I'm going to talk about, I'm going to make a slight adjustment. Right? And that is, after I commit P to the final solution and I construct my H, I will query H, but also hallucinate the rest of the edges and add them to my subgraph G2 that I'm constructing. So G2 contains all the edges that I queried and were realized. And also any edge that I'm not querying, I will add that to G2 independently with probability P sub E. Okay, why am I doing this? Because now G2 also comes from the same distribution as G star. And that gives me some interesting properties. So G1 and G2 are both from the same distribution as G star. So now both P and minimum vertex score of G2 are from the same distribution as opt. So clearly, again, it's a two approximation. It doesn't change the approximation ratio. Now having that, I will have an alternative per vertex analysis of this approximation ratio, which is for any vertex, I'll define CV to be the probability that this vertex is in the optimal solution. Okay, what's the optimal solution? Again, just minimum vertex cover of G star. We want to compare that with the probability that this vertex is outputted by this algorithm. Okay, so after you do the math, it's going to be 1 minus probability that is in none of the two solutions. Both of them, the vertex belongs to each with probability CV. Right? So it's going to be CV times 2 minus CV. So the per vertex approximation ratio, the way I define it for any vertex, would be 2 minus CV. Right?
You said they were the same distribution, but they're also independent?
Yes. So yeah, because these are something that I'm just, okay, the first one, G1, is just something that I'm constructing, right? The second one, some of the edges I'm querying, and the rest I'm hallucinating. So everything is independent.
But it's independent of G2 star, is independent of G1 star.
Yes.
Yeah. Sorry, Mahsa, can you say again why G2 star is independent of G1 star?
Okay, let's go back to the definition. So G1 is basically a random realization of G.
Yes.
Right? So G2 is is again constructed by querying some of the edges. Each one exists in G2 independently. Okay, G1 and G2, they don't have stars. Right? They are just realizations, right? So not great notation, but they are basically realizations. Okay, is it clear whether they're independent? Because
I'm worried because P is a function of G1.
yes.
H based on that.
So that determines which edges you actually query and which edges you hallucinate, right? Well, it doesn't impact the probability of the edges actually existing here. Okay, so G1 and G2 are just both realizations. Okay, now let's go back. So our per vertex approximation ratio, I define it to be the probability that the vertex belongs to the solution, the output, over the probability that the vertex is in the optimal solution. And that's 2 minus CV here. Okay. Now, what this means is that if, in some instance, CVs are large, this algorithm already beats half, right? So we need to come up with another algorithm that behaves the opposite, right? When CVs are small, we want an algorithm that also behaves good when CVs are small, right? So now let's go there. That's our second algorithm. Okay, let me say something before this. All the algorithms that I'm talking about, they have this commit then query approach, meaning that we first commit a subset P to the final solution, then query all the edges that are not that do not have an endpoint in P. Right? This is again follows the same framework. The only difference is the choice of P. Right? So here P only includes the vertices whose CV exceeds half minus some epsilon. Right? Again, there are 2 points we need to address. Why is H sparse, and what about the approximation ratio? The second part is easier. Okay, let's, yeah.
Why did we say that this is actually a vertex cover? Because
Yeah, so again, I'm just taking a subset of vertices. Okay, they will all be in the final vertex cover. Now I query any edge that doesn't have an endpoint there, right? Now I'm going to cover all of those also, and output the union of P and a minimum vertex cover of whatever that was realized.
So I'm kind of puzzled as to why this, where are we using the rest of these edges sampled independently with probability P sub B?
Okay, again, that is just for the sake of analysis. Alternatively, you can think of this as commit P, query all the rest of the edges, and then output the union of their minimum vertex cover as P. But what I'm adding here is that I'm also including any edge independently with probability P sub E to G2 to make G2 and G1 be from the same distribution as GSR.
Purely for analysis?
Yes, yes. Yeah, that's not needed.
Right.
Okay. The reason H is again sparse is very similar to what we had previously. Okay, let's first think about this. If an edge is in H, what does it mean? It means that it didn't have any endpoints in P, right? So if an edge has no endpoints in P, it means that the probability of the edge remaining uncovered by the optimal solution is at least 2 epsilon, right? How many such edges can we have? In the analysis of the first algorithm, I proved that if I take a random realization and its minimum vertex cover, the number of edges that are not covered are of n over P, right? So by linearity of expectation, the number of edges that will remain uncovered with probability at least 2 epsilon are O of n over P epsilon. Okay. Yep. O of n over epsilon P. Yeah. So this was just about the sparsity of H. Now we also need to talk about the approximation ratio. Again, the per vertex approximation ratio. Here we have the probability of V being in the output of this algorithm. and the probability of B being in the optimal solution. So anything, any vertex that has CV larger than half minus epsilon will be in the final solution, right? So that's going to be 1 over CV. CV is probability of vertex being the optimal solution. And for all the rest of the vertices, they only have a chance of joining S2 if they are in the minimum vertex cover of G2, which again happens with probability CV. So for the rest of them, this per vertex approximation ratio is 1. Okay. It's clear that both these terms, this is just one. This one, because it's only for vertices whose CV is larger than half minus epsilon. This is also always upper bounded by 2 plus epsilon. Okay. I'm just going to plot this function, this function. This is its plot. Okay. So for all the ones that have CV 0 to half minus epsilon, you get per vertex approximation ratio of 1. For the rest of them, it peaks at half. Right? So clearly, it's a half approximation ratio. Now let's compare it with the previous algorithm. Okay. So the previous algorithm, its plot will be this blue line. So now, as you see, for any vertex, at least one of these functions is at most 1.5 plus epsilon. Okay, you can verify that. So what this means is that if I could run different algorithms for different vertices, right, I could just get 1.5 approximation. I clearly can't do that, but if I could, it'd be amazing. Something else that I can do is to just run the best of these to see what happens, right? You can think of it like this. Let's let the vertices hold a weighted vote, right? Their weight is their CVs, and say which algorithm they prefer. If you do that, it gives, simply you can see that it's 1.75. But with the more careful analysis, we are able to show that just the best of these two is 1.66. But still, this doesn't push it down to 1.5. Okay, any questions so far?
So you could just run one of these two algorithms.
Yeah.
Tossing a random coin,
yes.
1.75.
No, you don't toss a random coin. You can calculate in advance what approximation ratio they're going to give you, right? Because you don't have any computational limitations. You have the stochastic information about the graph. You can calculate which approximation ratio each one's going to give you, and you can just do the best, right?
CV values that the algorithms are using, right? Like,
yeah. Those also.
like, are you assuming exponential time?
Okay, that's a good question. For CVs, we show that having a polynomial, you can call a minimum vertex cover oracle polynomial many times, then you will get an estimate of these CVs instead of accurate values, and that still works, gives us the same approximation ratio. But if you don't have any computational limitations, you can just calculate them exactly and decide which algorithm is best. Okay. Now, how much time do I have? Oops. Okay. So let's briefly talk about going down to 1.5. Okay. So the idea here is that I'm going to partition the vertices to two parts and kind of treat them differently. For the ones in the middle, I'm going to do something similar to algorithm 1, and for the red ones, I'm going to do something similar to algorithm 2. And how am I partitioning them? It's based on their CVs. Okay. I pick a threshold tau. And any vertex whose CV falls in here will be treated differently, and the ones whose CV falls here will be treated as if it's algorithm 2, okay? Again, I'm just not going to go over this part because, as I mentioned, our algorithms are commit and query. So the query part is clear. Let's only talk about which vertices you are going to commit in the first round. So as I said, here, it's going to be like algorithm 2. The red zone is like algorithm 2. How would algorithm 2 treat this? It will put all the vertices that have CV larger than half in the final solution and nothing from here. Right? Here, we treat them as if it's algorithm 1, which is we draw a random minimum vertex cover, we draw a random realization and its minimum vertex cover, and only a vertex joins P if it's in this minimum vertex cover. Right. Now, you may wonder, now, the subset of edges that you query, are they still, is this still sparse graph? And I'll answer that quickly, and the answer is yes, okay? So the claim is that any edge that joins edge here would either be queried by algorithm 1 or algorithm 2, because we know that both algorithms query O of n over p epsilon edges. It means that this algorithm also queries O of n over epsilon p edges. Okay, let's see why. But in analysis of the first algorithm, we showed that the expected number of edges not covered by a minimum vertex cover is O of n over p. And in the second one, we showed that the number of edges that have C, okay, here CE is the probability of the edge being covered by the optimal solution. Okay. So we know that the number of edges whose CE is smaller than 1 minus epsilon is also O of n over p epsilon. So my claim is that any edge that I'm going to query here falls in one of these two categories. First of all, if an edge has an endpoint in zone 3, it clearly will not be queried, right? So they either have both endpoints in zone 1 or 2. Okay. If both endpoints are in zone 2, it means that E is not covered by this minimum vertex cover. Right? So it will be also queried by algorithm 1. If it has at least one endpoint in zone 1, it means that the sum of endpoints, sum of CV of its endpoints cannot exceed 1 plus epsilon, 1 minus epsilon, right? So as a result of that, this edge would be also queried by algorithm 2. Okay. So the total number of edges this algorithm queries is a total sum of algorithm and algorithm 2. So it's still O of n over epsilon p. So I'm not going to talk more about the analysis, but to just briefly tell you about what I think about going beyond 1.5. As I mentioned, we show that if there are mild correlation between the existence of edges, to go beyond 1.5, you cannot do that by O of n over p, or the dependence on n cannot be linear. And to beat that, we need to heavily rely on the fact that edges are correlated. And our algorithm and analysis does not do that. The only where we use that in showing that the size of the number of edges that we query is O of n over p. In the analysis of our approximation ratio, we don't use that at all. And if someone wants to beat 1.5, they should do that. My intuition is that this algorithm cannot go beyond 1.5. So we need different ideas. And clearly, this is the main open question, but some other open questions is about both minimum vertex cover and matching, which are very closely related. And that is that using this optimal number of queries, what are the best approximation ratios that we get? For both minimum vertex cover and maximum matching, you need O of n over p to get any constant approximation. But these are the best known results that we have. We don't know whether you can go to almost optimal 1 minus epsilon and 1 plus epsilon for these using optimal number of queries. Okay, thank you. Yes.
How do we know that the vertex cover, the combination of the two outputs you constructed, is actually a vertex cover? Because what about the edges, the actual edges in the realized graph?
So we are following that commit then query framework. So basically what we are doing is that we are first committing these vertices to the vertex cover, and then I'll query any edge that doesn't have an endpoint here and also cover those. So just the framework itself ensures that the final solution is a vertex cover. Right? So you can just choose P, and in the choice of P, you need to make sure that H will be a sparse graph and that it gives you a good approximation ratio. Yes. No, I didn't prove it here. We proved it in our paper. Yeah. Okay. But I can tell you about it. It's not very difficult. I just didn't have enough time. Yeah.
Okay, let's thank the speaker again.
Thank you.